Hello everyone, this is Raiaan from Roots of Unity, and you are watching the third video in our Trigonometry series. This time, we're going to talk all about secant, cosecant, and tangent. We'll take a look at the relevant graphs, prove some identities, and also do some problem solving. In our previous video, we asked you to try and think of the reciprocal graphs for these trigonometric expressions yourselves. If you haven't, try and think about it again. So, we know that reciprocals refer to 1 divided by the function itself. So the point of the graphs where cos theta or sin theta equal to 1 or minus 1 stayed as such. The parts equating to 0 have now become vertical asymptotes. To sum it up, we just make continuous use of the fact that 1 by infinity equals to 0. By remembering just this much, we can figure out the rest of these graphs. Can you guess what the cotangent graph looks like? In this case, we know the original graph contained asymptotes. These asymptotes are now converted to points on the x-axis. Meanwhile, the points originally on the x-axis got switched to asymptotes instead. When a gradient in a tan graph decreases, it increases in the cot graph. The negative intervals stay negative and vice versa. Now, let's take a look at some relevant identities. Let's start with our trusty triangle. We know the sine cos tan relations already. The cosec or cot ones are just their flipped counterparts. So cosec is r by y, sec is r by x, and cot x by y. Moving forward, let's look at the Pythagoras theorem again. Divided throughout by x squared, we are left with a primary identity in trig, which is 1 plus tan squared theta equals to sec squared theta. If we divide it throughout by y squared instead, we obtain another crucial identity, which is cot squared theta plus 1 equals to cosec squared theta. You'll see these two identities quite often in trigonometry. However, this isn't the end of the list of identities in trigonometry. There's more to be covered soon. The problem solving with these expressions should feel familiar by now. Here are some questions where you're asked to find the exact values. Take a minute to think over them. Okay, so the first part asks for cosec 135. It's always convenient to start off these questions by reciprocating them. Sin 135 looks more familiar, right? Using the symmetry properties, we know it's the same as using sin 45. You could insert the exact value directly as we did in part 2, or find it out by drawing a right angled triangle. Since we already know two of the angles, the remaining angle here is also 45, giving us an isosceles triangle where we take the values of the sides as 1 unit each. Then, we can easily calculate the hypotenuse and hence find the value of cosec 135. We applied the same procedure in part 2 and 3. Part 2 made use of the symmetry properties again. Time to solve for theta. Keep an eye on the interval here. The first thing I did here is make use of identities and rewrite the expression in terms of cosec theta. Then we find the roots normally like we do using the quadratic equation. We rearrange again to find the equation in terms of sine 2 theta. Immediately, it's clear that 2 does not have a valid solution, so we work with minus 1 by 4. Our basic acute angle here is 14.5. Since sine is negative, we solve for third and fourth quadrants. Keep in mind that while the interval for theta is 0 to 180 degrees, the interval for 2 theta goes from 0 to 360 degrees. Hence, we divide the values by 2 to find 97.2 degrees and 172.8 degrees as the solutions. Next up, we'll practice curve sketching. This question asks you to sketch y equals to 1 plus cosec 1 by 2x within the interval 0 to 2 pi. It would be easy to sketch the general cosec x graph first. Since x here gets multiplied by 1 by 2, only half of the graph gets to be included in the interval. Cosec has a minimum at y equals to 1, so in this question the minimum is at y equals to 2. There you go. We'll end this video with one more identity question. How would you approach this? Firstly, you want to multiply both the numerator and the denominator with 1 plus sin x. Expanding expressions, we see that the denominator can be rewritten as cos squared theta. We divide each segment individually with the denominator. If we note the resultant expression carefully, we see that it can be factorized to tan x plus sec x whole squared, hence proving the LHS. And that concludes today's video. In our last video in this series, we'll cover the remaining identities within trigonometry and wrap up this topic. Thank you for sticking by.